start explaining, start taking the second part of the today's discussion. That is the revision class. That is chemistry and physics of surfaces and interface. So this is the 8-week course, and already all the. So I'll at first I will tell you to go by the all the problem solving classes, right? And before that, obviously, all 40 lectures you need to complete. I think you already completed that. But problem solving classes, I'm telling because these are the assignments, right? In these classes, I have solved the assignments and like the type of the questions that can be asked and how you can solve that questions. So so obviously, this can help you because I don't have any idea like who is going to set the question, because the questions that are set in the assignments are by probably the faculty. So this type of questions can be like you can expect that kind of questions in the classes. So I'll obviously suggest you to go by the all 40 lectures, because already you have what I feel you have already seen all the lectures. But if you have not seen the problem solving classes, I'll tell you that you should go by these classes, and you can get this class in this channel, YouTube channel, that is Tanmoy Khan PMRF IIT Kanpur is and all that. So this is the YouTube channel. They are all the classes where videos are there, and also from your announcements, sorry, not the announcement section, from your NPTEL website also. There you can get the Excel sheet, and you can have the access of all the classes, right? So I will first tell that. So after that, just the things to get you a hint of the things have been already covered in the course. So in the course, actually, these are the 2D kind of lattice. So in case in 2D, mainly translation, rotation, and uh, translation and rotation and reflection are possible. And depending upon these three things, normally there are five kind of uh, five kind of lattice are possible, that are oblique. Normally in oblique, a is not equals b, and also a gamma is not equals 90. And there are like five kind of point group as well. So you already know that. But what I am telling is that like if you have been asked like what is the parameter of a square, like, or some question is actually giving you a square kind of surface, so that you will have an idea of how the surface looks like. So these things you need to know. And also in case of 3D as well, these are the questions sometimes directly asked. So in case of monoclinic, what are the lattice parameter condition? So like that. So you need to remember these things. In case of hexagonal also, hexagonal is like frequently asked questions. Well, because cubic you don't need to remember. You already know. Monoclinic and orthonorm, tetragonal and hexagonal. These things have been frequently asked in several exams, right? So you need to have an idea about what are the lattice parameters condition, what are the angles condition to be like in the like specific kind of lattices, Bravais lattices. These are 14 kind of total Bravais lattice, depending upon the symmetry and also the filling of the atoms. So that between this 14, the things can be asked like the parameter of the hexagonal. In some assignment also, I think in assignment one or two maybe people have asked that question, that kind of question already. Yeah. Okay. So after that, what I want to tell is like this is I already told in the first problem solving session, session one, first class, that how Miller indices of a normal plane can be done, how a Miller indices for an HCP, like the hexagonal close pack system, can be done. Normally, in case of hexagonal lattice, normally instead of three in cubic, or the in case of cubic, normally HKL defines the Miller indices, and that is nothing but the H is nothing but the intercept. Let's say A, K is B, and L is 1 by C. Let's say what are A, B, and C? A, B, C are the intercept with the axis X, Y, and Z respectively, right? So, so whatever plane you are trying to assign with the Miller indices, that plane at what are the intercept with that axis X, Y, and Z, and just reverse it, like just the taken inverse of that, so that you will get about the Miller indices, right? Somebody is actually, the mic is on for somebody, or don't know, some kind of sound I'm getting. Okay, no problem. So these are the things in case of normal cubic system. We know about the Miller indices, how to assign it. But in case of hexagonal, there are different. There are another parameter, that is I, right? That is I. So, and I is not nothing but the minus of H plus K. So now this is A1, A2, and A3. So let's say we want to assign this plane. So this is my A1. Let's say this is my A1, this is my A2, and this is my A3, right? And this plane intercept is called as the, yeah, this is the let's say 0. So if you think about the basal plane, will be nothing but the, it is never never intersecting with this A1, A2, and A3. So it will be 0, 0, 0. But with this plane, it is actually cutting. So 0, 0, 0, 1, right? But in this plane, this is actually uh, intersecting that. Let's say this is A1 and this is A2 and this is A3. So A1 is this plane is intercepting A1 at 1, A2 at 1, but A3 at minus half, right? Minus half. Because this one is this direction is the plus 1, but this direction is, that means minus 1. So that means this is the minus half. And this plane is at infinite. This is the parallel with them. Sorry, this plane is at 1. So what will be the case? So 1 minus half, 1 by minus half means minus 2, 1, 1, right? Sorry, this plane is never intersecting, na? So this is at infinite. This is this is with the so this plane I'm talking about, the colored one. It is never intersecting this axis. It is parallel with this axis. Let's say this axis is Z. This is parallel with this Z axis. So that is going to be 1 by infinite. That means 0. And normally it is written as like this. So you just go by the problem solving session. There I have discussed it. Maybe I'm not right this time, but you can get it from the how you will decide. Then, depending upon the symmetry of the surface, or the symmetry of the surface, how the packing density changes. That is also very important. And these questions are normally, you can expect these questions in case of, and normally the packing density is higher in case of, highest packing density can be found in case of FCC 111, and that's why this plane is FCC 111 is the most stable, normally it is defined as most stable or least reactive, right? So whenever the packing density is high, that time the reactivity actually decreases. So you can find out like the packing density. That is also in the problem solving season 1 also I discussed, and in the first week lecture I think you can get it. Now this is the very important thing about chemisorption and resorptions, and that is also how the adsorptions, actually energetics of the adsorption. right? So let's say this is the surface and some adsorbent molecules are coming like this. So at first it will be physisorb, then it will be chemisorb, and chemisorb means some kind of bond formation is there. So it is like the case. So after also that kind of the structure of the absorbed molecules, how it will be is going to be determined by two forces. That is, sorry, that is add atom, or inter sorry, intramolecular force, intramolecular or intraatomic force, because add atom is interatomic. So intra force and add with the surface is called as the intermolecular force, or in, and that too is going to depend how my growth of the layer in the surface is going to be. So, and whenever the add atoms are concentration is very less, that time obviously the add atom and surface interaction is going to be there only. There will be no such add atom interaction. And after that, whenever we are going to add more and more coverage to the surface of the surface by the add atom, that time that intermolecular or interatomic attractions or the interatomic interactions are going to come into the play. And normally our surface, normally let's say this is the surface atoms, surface layer, let's say. So, and this is, let's say, the add atoms are going like this. Let's say this is FCC 100, and this blocks one are the add atoms, and the whole like the hollow ones are the surface atoms. So how one can define the surface, like how one can like represent the surface, that can be done by the Woods and the matrix notation. In the last class as well, at the very first of the last problems solving sessions, I already discussed, because some students have asked me about this Woods and matrix notation. So in the last class, I discussed about this Woods and matrix notation. So you can find it in the problem solving session 7, or also in the problem solving session 2, and Sarah also discussing these things in the second week. So let's say I am going to denote this by wood notation. So I need to find out the add atom unit cell by this by add atom unit cell, right? So this is going to be my add atom unit cell. So this is my add atom unit cell, and let's say this is the surface unit parameters are A. So these are square. So both of these are A. So this is the surface unit. Obviously, this is going to be the surface unit. This is A. So obviously from the picture you can see this is 2A and this is A again, right? This is A, but in case of my, so that means, let's say this is the add atom and this is the surface I'm writing. So surface lattice parameter is A cross A, and add atom lattice parameter is 2A cross A, right? So by Wood's notation, what we will need to do, we need to at first tell about FCC, the surface, then a hyphen, then the then the unit cell of the atom, the relation between the unit cell of the atom with the surface unit cell. So 2 cross 1. And then if the angle is there, but there is no angle, so that means that this will be the Wood's notation. But matrix notation is somewhat general, and they are only the, like, let's say A1 and A2 is the surface lattice parameter, and let's say B1 and B2 is the add add atom lattice parameter. So normally B1 is written as M1 A1 plus M2 A2, and B2 is written as M1, sorry, M11 1, yes, M1 to A1 plus M2 to A2, right? So normally this matrix M11, M12, M12 and M22 is going to give us the matrix notation. Similarly, FCC 100, we need to write FCC 100, then this. This is going to be going to give us the matrix notation. So these things I already discussed very carefully in these two lectures, lecture number 7 and in the lecture number 2, and also Sarah has discussed it very thoroughly in the second week classes. So I'll suggest you to go by this, because this is very important according to me, Like there will be questions from Woods and matrix notation. There is no way that it will not be there. And then the density or coverage of the surface. So depending upon the density or coverage of the surface, one can tell about the reactivity of the surface as a. So let's say, so this is these yellow atoms are the add atoms, and these blue ones are the surface atoms. So what is the density? Like number of atoms present in the add layer by number of atoms present in the surface. So let's think about this block cell. So in this cell, how many number of uh, surface atoms are contributing? So there is one, two, three, four corner share surface atom, means it will be shared by four nearby molecule, right? So 1 by 4. Now there are side shared 1, 2, 3, 4, and this will be shared by 2 atom. So half into 4, and there is one atom which is never shared with any other unit cell. So this is plus 1, right? This is for surface. Now if we try to calculate it for the add atoms layer, so there is 4. Let's say this is 1, 2, 3, 4. So 4 add atoms which are shared. So obviously corner shared, plus 1 add atoms which is not shared. So that means this is my add atom. Add atom unit cell. This is surface unit cell, right? So this is 1 plus 2 plus 1. That means 4. Total 4 atom of surface, and total add atom is 1 plus 1 is 2. So the density will be 2 by 4 or 0.5. Right. This is how density is calculated. And for any surface, you can calculate it like that. So this is the case. So you can easily do that. So I will suggest you to go by this. Then in the class, what is Moray patterns? That is kind of superlatives, and how the angle of this angle is going to determine the distance between distance of the superlatives parameters, how it is going to change. It is also discussed in assignment 3 and in the classes as well for the week 3. So this is very important, Moray pattern. And then strain, like depending upon the lattice parameter of the add atoms and the lattice parameter of the surface atom, how much the strain is there, and that strain is again going to determine the growth of the add atoms, what kind of growth in the surface will be. So in this case, let's both that copper, right? In copper surface, some CO molecule is cobalt molecule is like add atom, cobalt atoms is gaining, and in this silver surface same cobalt, and the lattice parameter for copper and CO are very similar, 2.55 and 2.51. So the strain is very less. In case of silver, the strain is very. So and that's why that strain is going to determine the growth, that Van der Meer or Stansky Carcinoma Nova is kind of like that. So the strain is going to, so how much the strain will be if the parameters are there. So you can easily calculate by using this formula, and I will suggest you to go to this kind of calculations. Okay, for strain, how to measure that, and what are the implication of strain on the surface growth. So normally these three kind of surface growth has been shown. That is Frank van der Merwe, that is layer by layer, that is Volmer-Weber, that is island formation, and Stansky-Kursanov is like both layer by layer as well as island formation. So in the very low coverage, that is the low coverage, all the growths looks like similar. But when the coverage grows, like at first in the layer by layer, the first layer actually completes, then second layer kind of formation. Then if we increase the coverage, then the second layer completes, then the third layer. So the one by one layer actually completes its growth, and then the other layer it is starting. So that is called Frank van der Merwe, or layer by layer growth, right? But in case of island formation, depending upon the, like, if the basically molecule interaction or the atom atomic interaction, atoms interaction is much higher than the surface, that times this kind of island growth is happening. And whenever the surface atoms interaction is higher than the atom, normally that island, sorry, the that layer by layer growth is actually occurring. And whenever that atom interaction is higher, that's why that one by one atoms are coming towards it. So whenever that is the case, that time island growth is actually observed. And in case of both the, like, both the island by island and layer by layer is forming in case of Stansky custom. So what are the regulating points? What are the things needs to be? So I'll suggest you to go to this, and also the problem solving session. Also, I tried to discuss a bit, right? So then normally we have learned about some techniques. Some techniques has been normally, and these are the very important, all the techniques. At first we started with scanning tunneling microscope and almost spent 1.5 week. Then from that, scanning tunneling spectroscopy and different kind of scanning tunneling microscope we have learned. Then we have learned about some XPS and UPS, that are nothing but photoelectron spectroscopic technique. Then in the last, again some scanning probe microscope technique. This is also scanning probe microscope technique. And they are also in the last week also we have learned about AFM, right? So all the things I also tried to give like try to give an introduction in my way in all the, for all the techniques. I also have in case of XPS also, in the last lecture I have given various model questions that can be asked from XPS. I am not sure that that will be asked or not, but I have tried in my way. So I'll tell you to go to that class and try to see that what are the questions can be asked, or like you can get an idea, right? But maybe that kind of questions may not be asked, but you can get an idea like how to solve a question practically, what should be the approaches, right? For all the techniques. So mainly in this case, actually, let me just erase this. So okay, it is visible. I'm going to erase this. Yeah. So this is a typical schematic diagram of STM. Normally, STM works with tunneling current, right? Tunneling current is measured. What is tunneling? That's also I given a lecture in the problem solving session, at first of the problem solving session or the last of the problem solving session. I also tried to tell about what are the factors that are going to control the tunneling current. So tunneling is nothing but the position where classically one thing cannot be accessible. So just the electrons are the quantum mechanical particle that can be accessed due to the quantum mechanical tunneling. And if we measure the tunneling current, and that will very highly depends upon the distance between the tip and the surface. So depending upon the topography, or depending upon the distance of the tip and the surface, that is going to change depending upon the topography. So that measuring the tunneling current, we can get the topography of the surface in an indirect manner. So that is what done in the scanning tunneling microscopy, right? That is what is done in the scanning tunneling microscopy. And then from that scanning tunneling microscopy, in a voltage, in a specific bias, we need to if we just calculate uh, the local length, like if we try to get the local density, we can get the idea of how the local density of state changes near the Fermi level. We can measure the band gap as well from using scanning tunneling microscopy, by applying different voltage and all. So that things have been very beautifully discussed in the lecture sessions. So I'll suggest you to go by that as well. Right. So this is what I have. Um, I already. This is the exact copy of the slide that I discussed in the classes when I solve the cases, right, of scanning tunneling microscopy. So this is the case when the bias is surface is positively biased. Normally, always the tip is grounded and surface is biased. So then some positive bias is there. So electrons are going towards surface from the tip. So this is the tip. So this is positively biased. Obviously, electrons will go from tip to the surface. When the positive bias, we like increase positive bias more and more. So more and more electron will go, right. So this is just nothing but the increasing of the positive. So that's why we are going to get more and more tunneling current. So that is going to be the case. And this is not directly ohmic contact. So the tunneling current is going to increase, but not in and not following the ohmic law. It will be like in this manner. So at a voltage, like just this IV plot is going to give me like we are going to get an IV curve. In case of negative surface is negative bias also, then that time the opposite thing will occur. That time from surface to tip electron will move, because this time the surface is negatively charged, so it is electron rich. So electron will go to the positive end of the like the tip. So and depending upon the bias, that is again going to be changed. So that then we are going to get this kind of IV curve in the whole regime, right? In the position in the positive bias, this is in the negative bias. And so this is the case, and from that we can measure the things, that is the local density of state, that is the band energy, binding energy of that state, and all things can be measured. Because if we just measure the di by dv, it is going to give us a change. So whenever there is a local density, let's say this is a local density, so that time, right? Let's say this is the local density. If it comes around this regime, so that time there will be a like increase in the voltage. So if we just like increase in the voltage. So if we just take a di by dv, so that time at that position we will going to get a peak. So that is actually telling us the binding energy of that local density and all. So this thing has also been discussed in the class very nicely. So I will suggest you to go by that process. And this is schematic diagram of photoelectron spectroscopy. That is nothing but using the photoelectric effect. So in the last to last class, I think in the problem solving session 6, I think I have tried to give a um, idea about the how what are the like photoelectric effects, how it depends, how it is discovered, and how things that comes whenever we try to discuss that thing, right? So so various things, like in case of different metal, how the photoelectric and the voltage curve will look like. In case of the intensity, if we change the intensity of the light, how it will going to be changed. How in case of the different energy light, how it is going to be changed. All things are done. But the process is photoelectric effect. That is nothing but there is a surface. We are exciting, like we are actually light is coming, and light has some energy that is new, and due to that, this is absorbing that energy, and due to that some electron is kicking out from the surface. And if we measure this electron's kinetic energy, we can tell about the binding energy of that several uh, like depending upon the energy of this, we can tell about the which electrons are kicking out, and that we can be analyzed to get the information. Normally whenever we use the UV light, that is called UPS, or ultraviolet photon electron spectroscopy, and whenever we use X-ray light, that time it is called XPS. That time X-ray photon is used. In case of UV photon, it is UPS. In case of X-ray photon, it is XPS. And normally UPS, that is lower electron. That time it is valence electrons are ejected. So normally density of state near the valence electron can be measured using this. And in case of XPS, as the energy is very high, energy very high, right? So core electron can be ejected. As the core electron can be ejected, so materials, oxidation state, elemental composition can be analyzed using this XPS technique. So this is a very good technique, overall good technique. Like STM was a single molecular technique. Sorry, this is single molecular technique because the tip is atomically sharp, so that we can get information from a small region or an atomic region information, but not the XPS or EPS. These are like average technique. Like this is not single molecular, but this is very important in terms of like getting an average picture of the material itself, right? And then in the last week, also I today in the first part I have discussed how the atomic force microscopy work. Again, I'll tell this. So what is this? This is a laser source. It is coming towards a cantilever, and the tip is in the cantilever. It is mounted in the cantilever. Now this cantilever is attached to a piezoelectric scanner, right? I mean, again discussing this part. So this tip is mounted in the piezoelectric scanner, and there is a laser source. There is a laser source. This is the laser source. Laser is coming, and this part of the this part of the cantilever, this is a reflection part. Like here, reflection of laser light, reflection plate, I mean, normally it is called. So from this part, actually reflection can occur. Now this reflected light is detected using a position sensitive photo detector. Position sensitive photo detector. What is photo detector? Photo detector is some detector when the light falls into that, some kind of voltage generates, right? Photo detector is nothing but due to the, it is also a kind of photoelectronic effect only. So whenever photon falls into that, electron comes back, comes out, and we measure the current. But position sensitive is like in all the positions we are going to get different kind of voltage, right? We are going to get different kind of voltage. Now this is connected to a controller feedback loop, and then it is actually into the, this is the surface or the sample that is in the surface can also be scanned, like it can also be scanned. So now what happens, now whenever it is in the contact region, like now let's say this tip is very near to this surface, right? Now the surface is having some kind of proportion. So whenever it is in here, now let's say the tip is maintaining same height. So in this position, the attraction or the repulsion, whatever, the interaction will be very high, and this position the interaction will be lesser than this. So to maintain this interaction or to maintain this constant force, this cantilever is going to deflect and change its position. Now, whenever the cantilever deflects, then in that time, light is, whenever it deflects, now light will deflect, point into some position, different position. So that time there will be a voltage drop created, and that voltage drop is going to the feedback loop, and the feedback loop is telling the scanner to change the position of the piezo. Then piezo is actually changing the position, and depending upon the changing the position, we are going to get the image of this place. And normally in contact mode, there are two kind of process. That is, there are actually three kind of mode. That is contact, non-contact, and intermittent contact. Right. Normally, imaging is done in contact mode, and in case of soft sample, it is done in the intermittent contact. And non-contact mode is not for imaging. Normally, electronic force, or magnetic force can be measured in case of using this non-contact mode. So in contact mode, normally whenever imaging can be done in two way, that is, one is constant height and one is constant force. This is constant. This is similar like STM. STM also works in these two mode, constant height and constant force. In case of constant force, normally whenever this tip moves from this place to this place, the height remains same, but due to the protrusion in the surface, the forces changes. And to maintain that, actually cantilever moves, like say, piezoelectric scanner moves its position, and then again maintain the same set voltage. So like that it works. And in case of constant height, the height remains same. Only the changes in the cantilever reflects in different position of the photodetectors. So that position in the photodetector actually directly give us the image. Right. So these are the things. Okay. So these are the things I wanted to tell. So if you have any questions, I try to tell you. Otherwise, I will stop here. Okay. And all the very best for your exam. Okay, if you have any question, you can ask, or otherwise, I'll stop here. Okay, then, Prakriti, all the best for your exam. I'll stop here, and thank you very much for your kind attention. Okay, thank you.